Deep in the darkness of interstellar space, racing toward our solar system at tens of thousands of kilometers per hour, astronomers have detected something that should be impossible, something that has never been observed in any solar system comet ever. We have always believed we understood the basic chemistry of these ancient comets, nickel and iron bound together since the formation of stellar systems, released together when solar heating awakens a comet's frozen surface. The 3E Atlas follows different rules entirely. Spectroscopic analysis reveals neutral nickel emissions streaming from this cosmic visitor, but the iron signatures that should accompany them are completely absent. However, pure nickel is a familiar phenomenon in terrestrial metallurgy, where it is obtained through refining. This raises a key question. Is this object a product of space manufacturing? While government space agencies speak in careful diplomatic language about safe trajectories and ongoing analysis, the preprint papers tell a different story. Tonight, we investigate what scientists aren't telling us about this interstellar visitor. We will examine the spectroscopic evidence, decode the institutional silence, and explore why some researchers whisper about possibilities that stretch far beyond conventional science. Prepare yourselves, we begin. Chapter 1. Nickel in the Dark. The cosmos has a way of keeping its most intriguing secrets wrapped in the language of spectroscopy. In the early morning hours of August 15, 2025, astronomers peering through the European Southern Observatory's Very Large Telescope in Chile noticed something that shouldn't exist. There, dancing across their computer screens in the form of precise wavelengths of light, were the unmistakable signatures of neutral nickel atoms streaming from Comet 3I Atlas. But here's what made seasoned scientists pause mid-coffee. The iron lines that should have accompanied those nickel signatures were nowhere to be found. In our solar system, nickel and iron are cosmic siblings. They form together, travel together, and when a comet heats up enough to release one, you almost always see both. It's like finding footprints in snow from only one boot. The universe, it seems, doesn't usually separate these metallic twins without a very good reason or a very unusual process. What makes this discovery particularly unsettling is not just the scientific anomaly itself, but the careful way it's being discussed in academic circles. When you read through the preprint papers posted on Archive, the platform where scientists share their findings before peer review, you'll notice something curious. The language is unusually cautious, even for astronomy. Phrases like mechanism uncertain and unusual physics or chemistry pepper the technical documents like diplomatic warnings. The instrument trail tells its own story. Teams using the ultraviolet and visual A-shell spectrograph and X-shooter instruments at the Very Large Telescope have independently confirmed these nickel emissions. They've also detected the emergence of cyanide, that's CN to chemists, in mid-August spectra. These aren't the kind of observations you misinterpret or accidentally fabricate. Multiple instruments, multiple teams, consistent results. Yet, if you scan the mainstream headlines about 3 Atlas, you'll find a curious disconnect. Some outlets hint at alien possibilities with the subtlety of a foghorn, while the actual scientific papers read like diplomatic cables, technically precise but emotionally sterile. The contrast invites a question. What exactly are we looking at when we stare into the spectroscopic soul of this interstellar visitor? There's another puzzle wrapped inside this cosmic riddle. 3 Atlas is shrouded in a coma. That's the fuzzy atmosphere around its nucleus, dominated not by water vapor like most comets, but by carbon dioxide. This CO2 shroud acts like a cosmic fog bank, making it nearly impossible to see the actual solid nucleus underneath. It's as if the comet is wearing a chemical cloak, revealing only what it chooses to show us. The James Webb Space Telescope has confirmed what ground-based observations suggested. This object produces carbon dioxide at rates that dwarf its water production, by ratios rarely seen in nature. For context, most comets are cosmic snowballs with a bit of dry ice mixed in. 3 Atlas appears to be the opposite, a dry ice ball with just a hint of snow. So, we're left with a series of interconnected mysteries. A comet that produces nickel without iron, a composition dominated by carbon dioxide rather than water, a nucleus hidden behind its own emissions, like a magician behind smoke and mirrors, and most intriguingly, a scientific community that seems to be choosing its words with unusual care. The guiding question that will follow us through this investigation is deceptively simple. Are we witnessing a natural quirk of cosmic chemistry and formation, or something that challenges our understanding of what's possible in nature? The evidence, as we'll see, doesn't yet point definitively in either direction, but it does whisper of possibilities that stretch the boundaries of conventional comet science. The cosmos, after all, has been whispering in nickel, and sometimes the quietest voices carry the most important messages. Chapter 2. Meet 3E Atlas. To understand why 3E Atlas has astronomers reaching for their most diplomatic language, we first need to understand what makes this visitor so fundamentally different from anything in our cosmic neighborhood. The designation itself tells a story. 3An marks it as only the third confirmed interstellar object ever detected passing through our solar system, following the mysterious cigar-shaped Wamakaimoa in 2017. The Atlas portion honors the asteroid terrestrial impactor Last Alert system, specifically the station at Rio Hurtado, Chile, where this cosmic wanderer was first spotted on July 1st. Picture the scene. Automated telescopes scanning the southern sky, their cameras capturing millions of points of light each night, when suddenly the computer algorithms flagged something moving with a velocity and trajectory that didn't belong to our solar system's gravitational embrace. The official designation reads CSI 2025 N1 Atlas, but the international astronomical community quickly recognized its interstellar nature and promoted it to 3I Atlas. This promotion isn't merely bureaucratic, it represents confirmation that this object originated somewhere else entirely, in a stellar system potentially hundreds or thousands of light-years away, and is now making what amounts to a one-time flyby through our celestial neighborhood. The mathematics of its trajectory tell an unambiguous story. 3 Atlas follows what astronomers call a hyperbolic orbit, a path so energetic that our sun's gravity can bend but not capture it. Unlike the elliptical orbits of solar system natives, this trajectory is open-ended, a cosmic highway that leads from interstellar space, around our sun, and back out into the galactic void. No return trips. No second chances for detailed study. From Earth's perspective, this interstellar visitor poses absolutely no threat. Its closest approach to our planet will be approximately 1.88 astronomical units, roughly 270 million kilometers away. To put this in perspective, that's farther than the distance between Earth and the Sun. Mars, during its closest approaches to Earth, gets within about 55 million kilometers. 3 Atlas will maintain a respectful cosmic distance, like a polite visitor who admires your garden from the sidewalk rather than trampling through your flower beds. The timing of its solar encounter adds another layer to this cosmic story. Perihelion, the point of closest approach to the Sun, is scheduled for around October 30th, 2025, at approximately 1.4 astronomical units from our star. That places it just inside Mars's orbital distance, close enough to receive significant solar heating, but far enough away to avoid the extreme conditions that might completely vaporize a small nucleus. Speed-wise, 3I Atlas is racing through our solar system at tens of kilometers per second relative to the Sun. Those racing through headlines you might have seen are technically accurate, but they can be misleading. This velocity is entirely normal for interstellar objects. What makes it remarkable isn't the speed itself, but the fact that this speed originated from motion through the galaxy, rather than from our Sun's gravitational acceleration. The timeline of visibility presents both opportunities and challenges for Earth-based observers. After perihelion in late October, 3 Atlas will appear to move closer to the Sun as seen from Earth, making observations increasingly difficult through November as it approaches what astronomers call solar conjunction, the point where it disappears behind the Sun's glare. However, this celestial game of hide and seek ends in early December 2025, when the comet emerges on the other side of the Sun for what may be our final extended observation period. One of the most frustrating aspects of studying 3 Atlas is how little we can directly observe of its nucleus. The Hubble Space Telescope, despite its extraordinary capabilities, can only establish an upper limit of approximately 5.66 kilometers for the nucleus diameter. This isn't a failure of our most advanced space-based observatory. It's a testament to how effectively the comet's own emissions obscure its solid core. Imagine trying to study a campfire by looking at the smoke rather than the flames. That's essentially what we're doing with 3 Atlas. The nucleus itself remains hidden behind its own coma, that fuzzy atmosphere of gas and dust that extends tens of thousands of kilometers from the tiny solid center. This observational challenge becomes even more significant when we compare 3 Atlas to its interstellar predecessors. 1I Oumuamua appeared to be largely inert, producing no detectable coma, despite its bizarre elongated shape and mysterious non-gravitational acceleration. 2I Borisov, on the other hand, behaved exactly like a solar system comet, complete with a beautiful tail and composition matching what we'd expect from our own Kuiper belt objects. 3 Atlas occupies a middle ground that's somehow more puzzling than either extreme. It's clearly active, producing the gas and dust emissions we associate with comets. But the chemistry of those emissions tells a story unlike any comet we've studied before, a story written in nickel lines without iron, in carbon dioxide ratios that dwarf water production, and in cyanide signatures that emerged precisely when theoretical models suggested they should. Chapter 3. The Carbon Dioxide Shroud. Most comets are cosmic snowballs with a secret. Beneath their dirty ice exteriors lies a chemistry dominated by water, the molecule that makes Earth's oceans possible, and life as we know it, thinkable. 3 Atlas, however, seems to have read a different script entirely. The James Webb Space Telescope's spectroscopic analysis reveals a coma dominated not by water vapor but by carbon dioxide, and in ratios that stretch the boundaries of what astronomers consider typical for these ancient time capsules. The numbers, while still being refined through peer review, suggest a carbon dioxide to water ratio of approximately 8:1. To understand how extraordinary this is, consider that most solar system comets produce water and carbon dioxide in roughly opposite proportions. It's like discovering a snowman made primarily of dry ice, with just a dusting of regular snow. Technically possible, but so unusual it demands explanation. This carbon dioxide dominance creates what we might call a cosmic fog bank. Unlike water vapor, which is relatively transparent at many wavelengths of light, carbon dioxide forms a dense, optically thick shroud around the nucleus. The result is that even our most sophisticated instruments struggle to peer through this chemical veil to glimpse the solid core underneath. It's as if 3 Atlas is wearing a cloak woven from its own emissions, revealing only what it chooses to show us. The FEREX mission's preliminary observations add another piece to this puzzle. Their imaging shows an extended carbon dioxide coma with no obvious jets or streamers, those characteristic features that usually point back toward active regions on a comet's nucleus. Instead, 3 Atlas appears to be outgassing uniformly from its entire surface, or at least in a pattern so symmetric that individual jets blend into a smooth, featureless glow. The Hubble Space Telescope's images reinforce this sense of concealment. What we see is essentially a dusty cocoon, with background stars stretched into trails due to the telescope's tracking of the comet's motion. The nucleus itself remains stubbornly invisible, hidden somewhere within that cocoon like a cosmic Russian doll, whose innermost layer refuses to be revealed. Several working hypotheses attempt to explain this carbon dioxide dominance, but each raises as many questions as it answers. One possibility involves the comet's formation environment. If 3 Atlas originated in a stellar system with a different temperature profile than our own, perhaps around a star cooler than our Sun, it might have formed near what astronomers call a carbon dioxide ice line. In such an environment, carbon dioxide would freeze out before water, potentially creating objects with compositions dramatically different from our solar system's comets. Another hypothesis focuses on thermal evolution and surface physics. Some comets develop insulating crusts over their lifetimes, layers of dust and processed organic materials that act like cosmic thermos bottles. Such a crust might suppress water vapor outgassing, while allowing the more volatile carbon dioxide to escape more easily. As 3 Atlas approaches the Sun, this selective outgassing could create the skewed chemistry we observe. The production rates themselves tell a story of a small but active nucleus, while the absolute numbers vary depending on the instrument and analysis method. A reminder that we're watching science in real time as calibrations are refined. The order of magnitude suggests a modestly sized object producing gas at rates consistent with its apparent size. There's nothing here that screams impossible, but everything whispers unusual. Media coverage has latched onto the cloak metaphor with enthusiasm, sometimes implying a deliberate concealment rather than a natural consequence of chemistry and physics. This linguistic choice reveals something about how we process cosmic mysteries. When nature behaves in unexpected ways, we tend to anthropomorphize the phenomenon, attributing intention where there may be only the inevitable result of unfamiliar physics playing out in an alien environment. The carbon dioxide shroud also complicates every other measurement we want to make: dust production rates, nucleus rotation periods, surface temperature mapping, the search for jets or active regions. All of these observations become more challenging when filtered through a dense, chemically active atmosphere. It's like trying to study a lighthouse bulb from inside a thick fog. You can see that something bright is happening, but the details remain maddeningly obscured. What makes this even more intriguing is the timing of our observations. Different instruments observing at different epochs can produce apparently contradictory results that later reconcile as we understand the temporal evolution of the coma. A spectrum taken in July might show one carbon dioxide to water ratio, while an August observation reveals a different value. Not because the measurements are wrong, but because comets are dynamic systems that change as they approach and recede from the sun. The carbon dioxide mystery deepens when we consider the implications for the nucleus composition. If the coma is dominated by carbon dioxide, what does that tell us about the solid ice mixture from which these gases are sublimating? Are we looking at a fundamentally different type of planetary building block? One that formed under conditions so unlike our solar system's early environment that it challenges our models of how planetary systems assemble? Or perhaps, as we'll explore further, the carbon dioxide shroud is telling us something else entirely. Something about processes that don't typically occur in nature, or about a visitor whose origins may be more exotic than even interstellar space usually provides. The fog bank surrounding 3 Atlas isn't just obscuring our view of its nucleus. It may be obscuring our understanding of what's possible in the cosmos itself. Chapter 4. The Official Line. When government space agencies speak about 3 Atlas, their language carries the careful precision of diplomatic communique. NASA's official statements read like a checklist designed to inform without alarming. Interstellar comet, safe trajectory. Perihelion, approximately October 30th, 2025. At roughly 1.4 astronomical units from the Sun. Closest approach approximately 1.88 astronomical units. No threat to our planet. The facts are presented with the emotional temperature of a weather report. Technically accurate. Reassuringly mundane. This measured tone isn't accidental. Space agencies learned hard lessons from previous encounters with unusual celestial visitors. The public reaction to 1A11's bizarre characteristics spawned everything from serious scientific debates about hydrogen icebergs to wild speculation about alien spacecraft. With 3 Atlas showing its own collection of anomalous properties, NASA and its international partners have apparently decided that conservative communication is the better part of valor. The European Space Agency echoes NASA's cautious approach, emphasizing the same safe distances and lack of threat to Earth, while noting the object's speed and late October perihelion timing. Their press releases read like exercises in measured reassurance, providing enough information to satisfy public curiosity while avoiding anything that might fuel speculative fires. The Minor Planet Center, which serves as the official clearinghouse for observations of asteroids and comets, has been similarly restrained. Their minor planet electronic circulars dutifully record astrometric observations, the precise positions needed to calculate and refine the object's trajectory, but avoid interpretive commentary. They're the cosmic equivalent of court stenographers, recording what happened without editorial comment. The Hubble Space Telescope program's public communications follow a similar pattern. Their Astronomy Picture of the Day feature shows the comet as a fuzzy blob against star-streaked backgrounds, with captions that emphasize the hyperbolic orbit and size constraints, while carefully avoiding speculation about the object's unusual properties. Even when presenting visually spectacular images, the accompanying text maintains a tone of scientific neutrality. This conservative approach extends to the James Webb Space Telescope team's blog posts and press releases. Despite conducting some of the most detailed spectroscopic observations of 3 Atlas, their public communications stick to safe harbor phrases: analysis underway, preliminary results, further observations planned. They link to preprint papers rather than making bold claims, letting the technical literature speak for itself while avoiding institutional endorsement of any particular interpretation. Behind this cautious public face lies a more complex reality. The same agencies funding detailed observations with the world's most advanced telescopes are clearly taking 3I Atlas seriously enough to dedicate precious observing time from instruments that are oversubscribed by factors of 10 or more. The James Webb Space Telescope doesn't point at random objects. Every minute of its operation represents thousands of dollars and months of competitive proposal processes. The visibility timeline adds urgency to these observations. 3 Atlas will likely become too close to the Sun for safe observation from Earth sometime in late September, remaining hidden behind solar glare until early December 2025. Chapter 5. The Lab Notes and Preprints. This creates a narrow window for detailed study before perihelion and another brief opportunity afterward. When the comet emerges from conjunction, the agencies know this is essentially a one-shot deal. Miss the opportunities this year and 3I Atlas disappears into interstellar space forever. What's particularly interesting is what the official statements don't say. There's no mention of the nickel emission lines detected by European Southern Observatory teams, no discussion of the unusual carbon dioxide to water ratios, no acknowledgement of the cyanide detections or their timing. This isn't necessarily secrecy. It's standard practice to let peer review processes run their course before making official pronouncements about potentially significant discoveries. The glossary-heavy nature of official communications also serves a strategic purpose. By carefully defining terms like perihelion, astronomical unit, coma, and production rate, agencies can provide education while maintaining focus on established science rather than speculative interpretations. It's a way of keeping the conversation grounded in measurable phenomena, rather than letting it drift into theoretical territory. Multi-observatory coordination tells its own story about institutional priorities. The James Webb Space Telescope, Hubble Space Telescope, and SFAREX missions have all been directed to observe 3 Atlas, suggesting high-level interest despite the measured public tone. When space agencies coordinate observations across multiple billion-dollar facilities, they're making a statement about scientific importance, even if they won't explicitly say so in press releases. The peer review timeline creates additional tension between public curiosity and institutional caution. Preprints appear on ARX within days or weeks of observations, but formal publication in peer-reviewed journals can take 6 months or more. During this gap, the most interesting findings exist in a scientific limbo, significant enough for researchers to share with colleagues, but not yet validated enough for agencies to stake their reputations on. Perhaps most tellingly, the absence of bold claims in official communications shouldn't be interpreted as evidence against extraordinary possibilities. Space agencies learned from Oumuamua that unusual objects can spawn unusual theories, some of which later prove correct, and others which prove embarrassingly wrong. In this environment, saying we don't know yet becomes both intellectually honest and institutionally prudent. The official line, in other words, may be less about what space agencies know and more about what they're willing to say, before the scientific process runs its complete course. While government agencies practice diplomatic restraint, the scientific community operates in a different realm entirely, one where curiosity moves faster than institutional caution, and discoveries are shared through preprint servers before bureaucratic approval processes can slow them down. In the case of 3 Atlas, this parallel universe of laboratory notes and preliminary findings tells a far more intriguing story than official press releases suggest. The European Southern Observatory teams, working with the Very Large Telescopes, UVAs, and X-shooter instruments have been remarkably forthcoming in their reflexive submissions. Their mid-August observations documenting neutral nickel emission lines without corresponding ion signatures represent the kind of finding that makes experienced spectroscopists double-check their calibrations. When multiple independent instruments confirm the same anomalous result, it moves from interesting if true to demanding explanation. The timing of these observations matters enormously. Early July spectra captured what amounts to a baseline 3 atlas at greater solar distance, with relatively quiet outgassing and conventional comet behavior. The mid-August observations as the comet moved closer to the Sun and its surface temperatures began rising showed the emergence of both the nickel lines and detectable cyanide emission. This temporal correlation suggests we're watching chemical processes unfold in real time, driven by increasing solar heating. An independent confirmation of the cyanide onset appeared in a September 3rd letter to the astronomy community, reporting the mid-August emergence consistent with very large telescope observations and additional confirmations from Lowell Observatory. When multiple research groups using different telescopes report the same temporal evolution of spectral features, it becomes difficult to dismiss as instrumental artifacts or calibration errors. The Farrick's preliminary note adds another dimension to this emerging picture. Their observations of an extended carbon dioxide coma with no obvious jets or streamers complement rather than contradict the spectroscopic findings. What we're seeing is a remarkably uniform outgassing pattern that produces unusual chemistry, carbon dioxide dominance, nickel without iron, and evolving cyanide production, all from what appears to be a small, featureless nucleus. These preprint submissions follow a well-established rhythm in astronomy. Observations are made, data are processed and analyzed, preliminary findings are shared with the community through ARX, and then the formal peer review process begins. This system allows for rapid dissemination of potentially important discoveries while maintaining the quality control that comes from expert evaluation. It also means that the most interesting findings often appear in technical papers months before they make their way into official agency statements. The production rate calculations illustrate both the power and the pitfalls of this preprint system. Different research groups using different instruments and slightly different analysis techniques can produce measurements that appear to disagree, not because anyone is wrong, but because the absolute calibration of production rates depends on assumptions about nucleus size, outgassing patterns, and atmospheric models. These apparent discrepancies usually resolve themselves as the analysis techniques converge and more data become available. What's particularly fascinating is how blog posts and informal commentary have begun interpreting these preprint results. Some analysis pieces suggest that the combination of unusual chemistry and hidden nucleus might indicate industrial processes or technological artifacts. These interpretations go well beyond what the data currently support, but they illustrate how quickly scientific observations can be extrapolated into speculative territory. The cadence of observations matters enormously for understanding comets, which are fundamentally dynamic systems. A spectrum taken in July shows one snapshot of chemistry and activity. An August spectrum reveals changes driven by increasing solar heating. September observations capture further evolution as the comet approaches perihelion. Only by combining multiple epochs can we understand the full story of how 3 Atlas responds to its changing thermal environment. Different instruments contribute different pieces of this puzzle. Ultraviolet and visible light spectroscopy excel at detecting metallic emissions like nickel and iron. Infrared observations from space-based telescopes can penetrate dust better and detect molecular emissions that are invisible to ground-based observations. Radio telescopes might detect molecules that don't emit invisible light. Each wavelength range tells part of the story, but the complete picture emerges only when all these observations are combined. The peer review process that follows preprint submission serves as both quality control and reality check. Expert reviewers examine methodology, question assumptions, and suggest alternative interpretations. This process typically takes months, during which preliminary findings might be refined, strengthened, or occasionally overturned entirely. In the fast-moving world of comet observations, where objects appear and disappear on timescales of months. This creates inevitable tension between scientific rigor and public curiosity. What emerges from this laboratory phase is a picture of three atlas that's simultaneously more detailed and more puzzling than official summaries suggest. The nickel detections appear robust. The carbon dioxide dominance seems real. The temporal evolution of chemical signatures follows predictable patterns driven by solar heating. But the underlying mechanisms that produce these observations, particularly the decoupling of nickel from iron, remain mysterious. The lab notes, in other words, are humming with activity and generating more questions than answers. And in science, that's often exactly where the most interesting discoveries begin. Chapter 6. Interpreting nickel, natural versus unnatural. The detection of neutral nickel emission lines in 3 atlases spectrum represents something like finding a single type of fingerprint at a crime scene. Technically clear evidence of what happened, but puzzling in its isolation. In solar system comets, nickel and iron emissions appear together with the reliability of a chemical law. When comets heat up enough to sublimate metallic grains embedded in their ice, both metals typically appear in spectroscopic observations because they form together in stellar nucleosynthesis and remain together through the planetary formation process. 3I Atlas breaks this rule, and the question becomes whether we're witnessing exotic but natural chemistry, or something that challenges our understanding of what's possible without technological intervention. The natural pathways for nickel-iron decoupling, while speculative, aren't beyond the realm of known chemistry and physics. One possibility involves selective volatility, the idea that under specific temperature and pressure conditions, nickel-bearing compounds might sublimate while iron-bearing compounds remain locked in solid form. This could occur if the comet's composition includes organic molecules that preferentially bind with iron, keeping it from escaping into the gas phase while allowing nickel to outgas freely. Another natural mechanism might involve surface chemistry driven by space weathering over millions of years in interstellar space. Cosmic ray bombardment and exposure to the interstellar medium could chemically alter surface materials in ways that change how metals are bound and released. If 3 Atlas spent significantly longer in interstellar space than typical Oort cloud comets spend between stellar encounters, such weathering could create surface chemistry unlike anything we see in solar system objects. The compositional heterogeneity hypothesis suggests that 3 Atlas might have formed in a stellar environment with different metallicity than our solar system. Some stars form with different ratios of heavy elements depending on their location in the galaxy and the composition of the molecular cloud that birthed them. A comet formed around a metal-poor star might naturally contain nickel and iron in unusual proportions, or chemical forms. Perhaps the most intriguing natural possibility involves carbonyl chemistry, in environments rich in carbon monoxide, which 3 Atlas appears to be given its carbon dioxide dominance and cyanide production. Transient metal carbonyls might form under specific conditions. Nickel carbonyl is a known compound that's more volatile than most iron carbonyls, potentially creating conditions where nickel escapes into the coma while iron remains bound to the nucleus. This mechanism remains entirely speculative and would require laboratory confirmation, but it represents the kind of exotic chemistry that might occur in unusual thermal and chemical environments. The unnatural pathway, stated clearly as a thought experiment rather than a conclusion supported by evidence, would require some form of technological processing that selectively concentrates or releases nickel. Industrial processes on Earth do create nickel-rich alloys and compounds with minimal iron content. Stainless steel production, electroplating, and specialized metallurgy all involve techniques that could in principle create materials with the chemical signatures we're observing. The question isn't whether such processing is possible, it's whether there's any evidence for it beyond the nickel detections themselves. A responsible evaluation of the engineered hypothesis would require multiple independent lines of evidence. Isotopic ratios that differ from solar system norms might suggest nucleosynthesis processes that don't occur naturally. Structured radar echoes could indicate geometric regularity inconsistent with natural objects. Non-gravitational accelerations with patterns that suggest propulsion rather than outgassing would be compelling. Radio emissions synchronized with the object's geometry might indicate artificial transmission. None of these additional technosignatures have been reported for 3 Atlas. The observational context matters enormously for evaluating these possibilities. Solar system comets do occasionally show unusual metal-line ratios, though typically not as extreme as the nickel without iron pattern observed in 3 Atlas. The decoupling isn't physically impossible, it's statistically unusual. This distinction matters because unprecedented doesn't automatically imply artificial, especially when dealing with objects from stellar environments that might differ significantly from our local chemical neighborhood. What would strengthen the natural case is reproducibility across multiple instruments and observing epochs, combined with theoretical models that can account for the observations without invoking exotic processes. If the nickel emissions continue to appear consistently as 3 Atlas approaches perihelion, and if the thermal evolution matches predictions from models of selective outgassing or unusual surface chemistry, the case for natural but exotic chemistry becomes more compelling. Conversely, what would strengthen consideration of technological origins would be the appearance of additional anomalies that collectively point toward artificial processes. A single unusual chemical signature might be explicable through natural means, but multiple independent anomalies that all suggest technological origins would be much harder to dismiss. The key word is independent. The anomalies would need to be explainable by technology, but not by any natural process. The commentary suggesting industrial nickel signatures represents interesting speculation rather than scientific consensus. Such ideas deserve consideration as hypotheses, to be tested rather than conclusions to be accepted, and they must be held to the same evidentiary standards as any other scientific claim. The burden of proof for extraordinary claims remains extraordinarily high, regardless of how compelling the speculation might be. Current observations provide one piece of a much larger puzzle. As 3 Atlas continues its approach to perihelion, additional data will either support or refute various hypotheses about its nickel emissions. Peer review processes will evaluate the robustness of the original detections. Cross-calibration between different instruments will test whether the observations are reproducible. Theoretical work will explore whether known chemistry and physics can account for what we're seeing. For now, the nickel whispers of possibilities without shouting conclusions, and in the careful language of science, whispers often carry more weight than proclamations. Chapter 7. Why Scientists Hold Back. The path from raw astronomical data to confident scientific conclusions follows a labyrinthine route that the public rarely sees, involving calibrations within calibrations, systematic error analysis that can take longer than the observations themselves, and institutional review processes designed to prevent the kind of spectacular mistakes that can end careers and undermine public trust in science. When it comes to 3 Atlas, this normally invisible machinery of science becomes particularly relevant because the observations are both technically challenging and potentially significant enough to reshape our understanding of interstellar objects. Consider the basic pipeline that transforms photons collected by a telescope into the spectroscopic signatures that drive scientific conclusions. First, the raw data must be calibrated against known standard stars to establish accurate wavelength and flux scales. Then, the sky background, including everything from atmospheric emission lines to scattered light from nearby sources, must be subtracted with mathematical precision. Only then can astronomers begin the process of identifying specific spectral lines and measuring their intensities relative to the continuum background. Each of these steps introduces potential systematic errors that can masquerade as genuine signals. A small error in wavelength calibration might shift an apparent nickel line to a different element entirely. Incomplete sky subtraction could create false emission features or suppress real ones. Continuum placement, determining what counts as the baseline against which emission lines are measured, can dramatically affect the apparent strength of weak spectral features. When claims of unusual chemistry rest on precisely these kinds of measurements, extraordinary care becomes essential. The telescope time allocation system adds another layer of institutional caution. Observing time on facilities like the Very Large Telescope or James Webb Space Telescope is awarded through competitive processes that can take months of preparation and review. When astronomers receive this precious resource, They typically have proprietary periods during which they can analyze their data without external pressure. This system encourages thorough analysis rather than rushed conclusions, but it can also create frustrating delays between observations and public announcement of results. The signal-to-noise ratio considerations become particularly critical when dealing with weak spectral features near the detection threshold. The same dataset can appear to show strong emission lines or no emission at all, depending on how the analysis is conducted. Different continuum fitting techniques, different methods for combining multiple exposures, even different software packages for data reduction, can yield seemingly contradictory results from identical observations. Multiple independent teams must verify unusual claims before the scientific community accepts them as robust. Reputation and replication concerns loom especially large in the aftermath of the 1AR rumor Erupts, where initial observations of an unusual acceleration spawned theories ranging from hydrogen icebergs to alien spacecraft. Some of those theories were eventually supported by additional analysis, while others were quietly abandoned as better data became available. The experience taught the astronomical community that interstellar objects can generate intense public interest and scientific controversy in equal measure, making careful evaluation of claims more important than rapid announcement. The peer review process, while often frustratingly slow, serves as quality control that can catch errors invisible to the original research teams. Expert reviewers examine methodology, question assumptions, suggest alternate interpretations, and occasionally identify systematic errors that invalidate entire analyses. This process can take months or even years, during which preliminary findings remain in scientific limbo, interesting enough to discuss among colleagues, but not validated enough for institutional endorsement. Observing geometry adds temporal complexity to these systematic concerns. The apparent strength of spectral lines depends not just on the physical processes producing them, but on the viewing angle, phase angle, and distance between Earth and the comet. An emission line that appears strong in July observations might seem weak in August data, not because the underlying physics has changed, but because we're viewing the same process from a different perspective or at a different distance. Inter-instrument cross-checks provide essential validation, but require careful attention to systematic differences between facilities. The Very Large Telescope's UVS instrument operates differently from the X-shooter spectrograph, which in turn has different characteristics from space-based instruments like those on James Webb or Hubble. Confirming a detection across multiple instruments requires understanding how each facility's unique systematic errors might affect the apparent strength or wavelength of spectral features. The James Webb Space Telescope team's blog posts exemplify this institutional caution. Despite conducting some of the most detailed observations of 3 Atlas, their public communications stick to phrases like analysis underway and preliminary results. They link to preprint papers rather than making institutional claims, letting technical literature speak for itself while avoiding situations where the space agency might need to retract or revise public statements if peer review reveals problems with initial analyses. Visual representations of the same data can tell dramatically different stories depending on processing choices. The same spectrum can be made to emphasize weak emission lines by expanding the vertical scale, or to de-emphasize them by showing the full dynamic range of the data. Different continuum fits can make emission features appear or disappear entirely. When dealing with potentially significant discoveries, researchers must ensure their data presentation choices reflect the genuine strength of the evidence rather than their hopes about what the data might show. The bottom line is that scientific caution doesn't indicate cover-up or conspiracy. It reflects hard-won wisdom about how easy it is to fool ourselves when dealing with complex data near the limits of instrumental sensitivity. In astronomy, where objects appear and disappear on timescales that don't accommodate lengthy analysis, this creates inevitable tension between scientific rigor and public curiosity, but it also ensures that when astronomers do make strong claims about unusual objects like 3 Atlas, those claims rest on foundations solid enough to support the weight of extraordinary implications. Chapter 8. Media versus Methods. The chasm between how scientific discoveries unfold in laboratory notebooks and how they appear in public media represents more than just a translation problem. It reflects fundamentally different approaches to uncertainty, evidence, and the pace at which knowledge should be constructed. When 3 Atlas began showing unusual spectroscopic signatures, this disconnect became particularly stark, with sensational headlines competing against methodical data analysis in what amounts to parallel universes of information. Consider the spectrum of media coverage that emerged as preprint papers began appearing on ARXiv. At one extreme, tabloid-style outlets seized on the mystery aspects with headlines that practically vibrated with excitement. Alien craft, disguised as comet, baffles scientists. Read one particularly breathless example, transforming careful spectroscopic observations into science fiction scenarios with all the subtlety of a carnival barker. These outlets treated every unanswered question as evidence of conspiracy, and every cautious scientific statement as proof that authorities were hiding dramatic revelations. More responsible science journalism struck a different balance, emphasizing the carbon dioxide dominance and unusual chemistry while acknowledging the limitations of current data. Publications like Live Science and Smithsonian Magazine managed to convey the genuine scientific intrigue without veering into speculation unsupported by evidence. Their articles explained why a carbon dioxide-rich coma matters, what nickel emission lines tell us about comet composition, and why scientists speak cautiously about preliminary findings. NASA and European Space Agency press releases stick religiously to established facts, orbital parameters, safety assurances, observing schedules and instrument capabilities. Their language carries all the excitement of a technical manual, which serves the important function of providing accurate information while avoiding the kind of speculation that can later prove embarrassing if contradicted by additional data. This institutional conservatism creates information gaps that speculative coverage rushes to fill. When official sources limit themselves to analysis ongoing and further observations planned, more adventurous outlets feel free to explore possibilities that range from exotic chemistry to technological artifacts. The problem isn't necessarily that such speculation occurs. Science often advances through bold hypothesis, but that speculation and established fact can become confused in the public mind when presented with similar levels of apparent authority. The alien craft hypothesis provides a useful case study in how scientific caution gets interpreted through different media filters. The actual evidence consists of unusual, but not impossible chemistry, an obscured nucleus, and outgassing patterns that differ from typical solar system comets. Responsible reporting presents these as interesting anomalies worthy of further study. Sensational coverage transforms them into smoking guns for extraterrestrial technology, as if the absence of conventional explanations automatically implies artificial origins. Social media amplifies these distortions through mechanisms that prioritize engagement over accuracy. Dramatic claims about alien visitors generate more clicks, shares, and comments than careful discussions of spectroscopic calibration. The algorithms that determine what content gets promoted have no built-in preference for scientific rigor, creating an information ecosystem where the most exciting interpretations often drown out more measured analysis. Even reputable outlets face challenges when reporting on evolving science. Carbon dioxide to water ratios reported as approximately 8:1 in early coverage might be revised to 6:1 or 12:1 as calibration methods improve and additional data become available. These revisions don't indicate that the original reporting was wrong. They reflect the normal process of scientific refinement, but they can erode public confidence in scientific claims if the iterative nature of research isn't clearly explained. The confirmation bias problem works both ways in this media ecosystem. Outlets that lean towards sensational coverage tend to emphasize any new data that supports exotic interpretations, while downplaying findings that suggest conventional explanations. Conversely, more conservative outlets might underemphasize genuinely anomalous findings to avoid appearing credulous. Both approaches can distort public understanding by filtering complex reality through predetermined editorial positions. The peer review timeline creates additional complications for media coverage. Preprint papers appear on ARG within days or weeks of observations, providing immediate access to technical findings, but without the quality control that comes from expert evaluation. Journalists working under deadline pressure might report preliminary findings as if they carry the same weight as peer-reviewed conclusions, creating situations where later revisions or retractions can seem like scientific flip-flopping rather than the normal evolution of understanding. Language itself becomes a battlefield in this process. When scientists write about unusual chemistry or mechanisms not yet fully understood, they're expressing appropriate caution about phenomena that don't fit established models. When media outlets transform this language into baffling scientists or defying explanation, the emphasis shifts from ongoing research to complete mystification, implying that the scientific process has reached a dead end rather than an interesting beginning. The trust tier that emerges from this analysis suggests a hierarchy of reliability that informed consumers can use to navigate conflicting reports. Primary sources, observatory press releases, peer-reviewed papers, official space agency statements occupy the top tier, representing information that has passed through institutional quality control. Secondary sources, like established science journalism outlets, provide valuable interpretation and context, but with varying degrees of speculative content. Commentary and opinion pieces, regardless of their quality, represent personal interpretations that should be clearly distinguished from established findings. Perhaps most importantly, media literacy in the context of astronomical discoveries requires understanding that we don't know yet often represents the most honest statement scientists can make about ongoing research. This phrase doesn't indicate failure or cover up. It reflects the careful process by which durable knowledge gets constructed from incomplete information. In a media environment that rewards certainty and dramatic revelation, such intellectual humility can seem unsatisfying, but it may be the most valuable information of all. The challenge for consumers of science media lies in learning to enjoy mystery without demanding premature resolution, to appreciate the complexity of real research without losing interest when answers don't arrive on news cycle timelines. 3I Atlas will continue revealing its secrets on a schedule determined by orbital mechanics and observational opportunities, not by editorial calendars or social media trending topics. The worst-case scenario for 3I Atlas sounds insane until you consider this. What if it's not leaving? What if this flyby trajectory is actually a deceleration maneuver, executed by technology we can't detect? Imagine an intelligence so advanced that mimicking natural orbital mechanics is child's play. A civilization that deploys surveillance assets disguised as comets, asteroids, even space debris. 3 Atlas's unprecedented speed and impossible chemistry might be signatures not of alien formation, but alien intention. As it approaches perihelion, hidden systems could be powering up, preparing for the next phase of whatever mission brought it here. Tonight we'll venture into the speculative shadows, where natural explanations crumble and cosmic paranoia takes root. The question isn't whether 3 Atlas will leave, it's whether we'll recognize when it decides to stay. Part 1. Is 3 Atlas a threat? On July 1, 2025, Chile's Atlas telescope detected something extraordinary. A speck of light with a hyperbolic trajectory that could only mean one thing. This visitor came from another star system entirely, designated 3 Atlas, formerly C2025 None. It represents humanity's third confirmed interstellar object, following Oumuamua in 2017 and Intwenai Boris in 2019. But what if this third visitor carries implications far beyond the first two? Implications that stretch the very definition of worst-case scenario. Unlike solar system natives bound by elliptical orbits, 3 Atlas traces a hyperbolic path through space. Its orbital eccentricity exceeds 1 node, marking it as definitively unbound to our sun's gravitational influence. Racing inward from the constellation Lynx at unprecedented speeds, it will reach perihelion on October 29th, at over 130 mph, fast enough to cross the United States in under 3 minutes. Yet beneath these reassuring mathematical certainties, a nagging question persists. What if the true worst case isn't about where it's going, but about what it might reveal about us? Despite this dramatic velocity, 3I Atlas poses absolutely no threat to Earth. Its closest approach in mid-December will be approximately 18 astronomical units away, about 270 million kilometers, nearly twice the distance between Earth and Mars at their closest. NASA's position is unequivocal. This is a natural comet, not an artificial craft or hazardous object. But when we venture beyond NASA's careful language into the realm of speculation, what shadows might this ancient wanderer cast on our assumptions about intelligence, purpose, and cosmic coincidence? The Hubble Space Telescope has been monitoring the visitor since discovery, revealing classic cometary behavior as solar radiation sublimates ices within its nucleus, creating a glowing coma. The James Webb Space Telescope captured spectra on August 6, showing unusually high carbon dioxide concentrations, a chemical signature that speaks of alien formation conditions unlike anything in our solar system. Yet, this chemical oddity raises an uncomfortable question. What if 3I Atlas's true significance lies not in what it is, but in what it forces us to confront about what we don't know? Ground-based observatories worldwide have joined the effort, with radio telescopes finding only natural emissions and silence where artificial signals might hide. This coordinated response represents modern astronomy at its finest, a global network confirming both the object's interstellar origins and its harmless trajectory. But what happens when we push beyond the comfortable boundaries of harmless and consider scenarios that challenge not our physical safety, but our fundamental understanding of our place in the universe? The discovery frequency suggests space teams with such wanderers, debris from planetary formation around distant stars flung into the void by gravitational violence, and condemned to wander for billions of years. Each teaches us something new about the galaxy beyond our sun's influence, though none threatens our world's safety. Yet, if the galaxy is indeed filled with these ancient messengers, what are the implications when we dare to speculate beyond the scientific consensus? As The Guardian aptly noted, 3I Atlas is a cosmic curiosity, not a catastrophe, a reminder that we inhabit a universe far stranger and more connected than daily life suggests. This ancient visitor offers us a brief window into galactic deep history, carrying secrets from stellar neighborhoods we can barely imagine. But what if the real mystery isn't what secrets it carries, but what secrets it might unlock about the true nature of interstellar visitors and the speculative scenarios that lie beyond the reach of telescopes? Part 2. Speed, size, age, a quiet powerhouse. The numbers alone stagger the imagination. 3I Atlas moves at over 130 mph, roughly 150 times faster than a high-powered rifle bullet. Its hyperbolic excess velocity of 61 km/s represents the speed it maintains, even accounting for solar gravity, unchanged by eons of galactic wandering. But when we consider what such incredible speeds might enable in speculative scenarios far beyond current scientific understanding, what possibilities emerge that could redefine worst case entirely? This velocity dwarfs its interstellar predecessors. Oumuamua traveled at 26 kilometers, while 2I Boris managed 32 kilometers. 3 Atlas moves nearly twice as fast, suggesting either violent ejection from its birth system or acceleration through multiple gravitational encounters during its cosmic odyssey. Yet, what if this progressive increase in velocity across 3 interstellar visitors hints at something more deliberate than random cosmic violence? Something that pushes us towards speculative territories our instruments cannot explore. Determining size proves challenging due to the glowing coma that obscures the nucleus. Current estimates range from 0.3 to 5.6 kilometers in diameter, anywhere from 3 football fields to a small mountain. The uncertainty stems from assumptions about surface reflectivity and coma production efficiency. Smaller estimates seem more likely based on typical comet parameters, though even at 0.3 kilometers, we're discussing a substantial object. But what if the very uncertainty that frustrates our measurements conceals possibilities that extend far beyond questions of mere size? This size uncertainty raises fascinating questions about survival. How could such a relatively modest body endure ejection violence,